Okay, so let's start this week's program. So we have several talks. There are some kind of requests that we should not have too many talks, but so this week we still have some number of talks. And one reason is, of course, that we are trying to communicate with each other from people from different groups. And this week we will have three kinds of lecture by Professor Abhishek Dhar from ICPS in India, Bangalore, and he's going to talk about fluctuating hydrodynamics for spin chain. Yeah, of course, he's one of the leading experts in the subject, and he's ready to paper on anomalous diffusion and transport. This is quite well-known literature. And today he's going to talk about last week we had a lecture by Hugo to check on large deviation. And his lecture was mainly for finite degrees of freedom. But today, this week, I think Abhishek is going to talk more on many degrees of freedom, what is infinite degrees of freedom, and how fluctuations are important for non-trivial network. So please start.
Thanks for the introduction and for the invitation and all the other organizers. Okay, so Tumur asked me that I should talk about something which kind of connects the non-trivial and the other living matter communities. So what I thought is that something about spin change would be interesting to people in living matter community. So it's actually I saw that this book by Chaitin and Lubensky, for example, the chapter on hydrodynamics starts with rotor chains and spin chains. And what I'll talk about is kind of connects to that chapter, and maybe the interesting thing that one can learn from what one observes in the spin chains that I talk about. Okay, so the sort of the plan of my three lectures are so what I'm really going to do is try to so I'm going to talk about anomalous transport. Even what the meaning by that. Okay. So I'll talk about anomalous transport in spin chains, but basically what I'll try to show is that there's some sort of nice connection between anomalous transport in harmonic oscillator chains, which has been known for quite some time, and what we see in spin chains. Okay, and this connection we'll basically understand using the framework of nonlinear. Okay, so so the first lecture, today's lecture, I will mostly talk about harmonic oscillator chains and how one uses nonlinear fluctuating hydrodynamics to understand anomalous transport in this system. And then in the next two lectures, I'll talk about how this that one connects it to spin chains. Okay, so so the models that I'm looking at, so let me just first talk about exactly what kind of models that I'm talking about. So for oscillator chains, I look at collections of particles. So let's say this is and each particle has a position X and a momentum X. And it's a Hamiltonian dynamics. Is unit mass particles, and then there's some interaction to the this nearest neighbors. Okay, and this interaction could be so one of the popular models is something called the Fermi-Pascal chain, where the interaction is given by let's say, so this is known as the Fermi-Pascal, and there was a fourth person as you know who did all this simulation. So now nowadays it's called executive model. Okay, so this is sort of very old model, but it's and it's well known in the context of fractions of thermalization and so on. But we won't be worried about that. What we want to understand is the hydrodynamic description of this system. Okay, so this is what I talk about when I talk about harmonic oscillator chains. These are the kind of systems, and then spin chains. We'll basically look at rotor models. So in this case, there's an angle at every there's a lattice, and there's an angle at every side, which I call phi x, and the interaction is that it tries to align them, and then there's a kinetic energy or angular momentum part, and again the dynamics is purely Hamiltonian. Okay, and then what I look at is so again in lattice at each side there's a spin is where is one, and the interaction that and it's an accepted interaction that the delta term in front of the interactions, and so okay, so there's a minus sign when looking at the ferromagnetic case. This is everything I talk about is classical. Maybe in the last lecture I talk about there's a lot of interesting results in the quantum case for spin chains. But so far everything is classical. And the dynamics here, okay. So here it's just a simple Hamiltonian dynamics. And here also it's because of this constraint there are effectively 2 degrees of freedom at each side. And as I'll show later, this is also can be written in this usual Hamiltonian form. But the other sort of more popular way to write it is the spin precision dynamic, which is the local spin or local magnetic field like that. Okay, so this is the spin precision dynamic. And this like it's also has exactly the same Hamiltonian structure as on the other.
Yeah, technical form to type X this spin chain we are not integral about quantum case, but
it is non-integral.
non-integral.
Yeah.
What about boundary conditions? What do you mean by the chain?
Okay, so eventually I'll mostly talk about like sometimes when I talk about finite systems, I'll talk about the boundary condition, but usually I'll be talking about infinite systems.
So you don't have to have some properties of regularity or something
At the boundaries.
boundary.
So like you say as when n is large or.
Right, yeah. So when n is large, I don't worry. I mean, I don't have to worry about conditions. In some cases, boundary conditions will be important if it's a finite.
What is the line? Over the screen?
Oh, sorry, this is an X.
Oh, just
vector and it's the lattice size. X is the lattice.
And that's it's squared. You put it one way. So
A square is one, right? Yeah.
and for model A, all the masses are the same.
All masses are equal. Okay. There are other models where you take like for so one of the other sort of popular models is a hard point gas, where there's no strings, but they just interact on collisions. There, sort of to make the model non-integrable, you take like the masses to be different. That's another sort of problem. But one we will just stick to this. Okay, so now I'll talk about what does if I just stick to this FQ team harmonic and harmonic chain. I'll tell you what anomalous transport is and how one understands it using this framework of fluctuating hydrodynamics. At each side, right? Sorry. And maybe I'll just push it up. Oh, no, sorry. No.
That's the way. Yeah, back. So we can- This is the best time.
Thanks, buddy.
I know that this
So, okay, so I mean, so what are the observations of anomalous transport in this activity chain? So there are sort of two main observations. One is in a non-equilibrium setup. So, so this is the first observation. Okay, so I mean, one of the first studies that was done in this course is in the context of understanding heat transport. So one takes this chain of particles and you basically connect it to heat paths at different temperatures. So I'll tell you how you do that. So this T left and T right. And so this you can do by, so in this case, you look at a finite chain of so x goes from 1 to n. And let's say the first particle you connect, you also add a Langevin dynamics. So you add some term like minus gamma x. And similarly, you add your Langevin term at the right end. So, so you have some Langevin dynamics, and you look at the steady state. Right? So, and in the steady state, measure heat current. So now, also what is heat current? So this system, the Hamiltonian, is it can consider as some local energy terms. Where it's just And so this is like a local energy. And if you take like if you ask how does this change with time, you can see that this has the form of continuity equation because it's locally conserved. So we know what is the current operator, and in this steady state, you can just measure the current anywhere. So if you do that, so that's the steady state heat current. So this when you just measure GRX in the so one question is if it's normal transport, what you expect is that the current should follow sort of Fourier's law. So, and if that is true, then you can ask how does it scale as you increase the number of oscillators, and you expect that it should go as 1 by n. And what you find is that, okay, so this is what the Fourier would predict. But what you find is that, so this is not true, and you find that it goes as 1 by n. This is one of the first signatures of angular transfer. Okay, so now, like how does one understand this sort of anomalous transport? And one of the ways one would think is to try to use like what we know from linear response theory, which gives us the thermal conductivity in terms of current condition. So, and that leads us to the second observation. So this is the first observation. You just look at the non-equilibrium steady state and you find something like this. And the second observation is look at so one can find total current operator. And what Green Kubo tells us is that the thermal conductivity, if Fourier's law was true, then the thermal conductivity is given by efficiency factor and so and then you have to take large n and okay, so in this case you might wonder, so since you get Fourier's law is not valid, which that means the thermal conductivity is doing something funny. So you compute this current correlation in equilibrium. Then the observation is that so this is P of P of the function T. So you find that so it's a very slow decay, and which makes this blow up. Right? So this becomes infinite, and that's the.
Does it depend on the details of the potential?
It's more or less universal, and there is some very like generically you'll get to the for some yeah some so which I'll talk about later. When
But when you say equilibrium, steady states here, you said equilibrium average.
yeah, this is in the equilibrium. Yeah, there's no.
There's TL is with TI.
But this one is like without any bar. It's isolated system.
Okay.
So this is for the complete isolated system. Okay. Okay. So this is the second signature, and then the third sort of related signature is of course like. Anomalous heat transport basically means that if I look at spontaneous fluctuations, they should spread anomalously. So one can look at, for example, I can look at energy. If I look at fluctuations in energy in equilibrium. So if I compute this kind of space-time correlations in equilibrium again. no heat paths, then so if it was diffusive, I would expect this to spread diffusively. But in this kind of system, one finds that there is some energy fluctuations spread sort of non-diffusively. Okay, so for the generic case, this new value is so mu is in fact 3p. This is non-Gaussian, and in fact it's a Levy distribution. Okay, so this is I would say the third signature. There are other signatures which I won't talk about, but these are the three main features. Okay, so now one would, given that you can see this in this anomalous behavior in correlation functions, this means one can try to understand it using hydrodynamics. And so that's the sort of goal of fluctuating components. So how can we understand this sort of anomalous correlations using hydrodynamics? Okay, so yeah, so let me do that. Okay, so one thing maybe is worth mentioning is that in this case, okay, so what are the conserved quantities? There is energy of project conserved, and apart from that, momentum is also conserved. Okay, so this momentum conservation is very important because if I, for example, if I add on-site potential, then one immediately gets Fourier's law. Okay. So, so that's important that momentum is conserved. And so then we have to write hydrodynamic equations including momentum.
I'm sorry, and one thing that if you set alpha and beta to 0, you don't everything is fine. You don't get anomalous transport.
No,
Yeah.
sorry.
Yeah.
You get ballistic transport. So you don't get Fourier's law.
Yeah.
It's just ballistic.
Yeah.
So the current would be independent of system size for you.
Yeah.
Okay, so so now okay, so linear fluctuating hydrodynamics. So first, let's ask what are the conservation laws? So this is, if you think of it, so there are two ways of writing hydrodynamics. You can either think of it as a fluid, in which case, one would immediately see that number momentum and energy are the only conserved quantities. So typically for generic potential, you don't expect any other conservation laws. This will give rise to three conserved fields. So, so these equations will give like sort of Navier-Stokes equations for the 1D fluid. But another way to write is using lattice variables. So in which case we so here X would be like if I a chain of particles, then X would be the so in usual hydrodynamics X would be the location in space. But now I look at a description where X is the particle level. We'll call this capital X. So that's exactly the particle level, and that's going to be my field variable. Okay, and so in this description, the lattice description, yeah, so it's the conserved fields are basically so instead of density, one looks at the volume or the stretch, like that's kind of inverse of the density. So the first conserved quantity just so this is the first conserved field X. And then momentum is E of X and energy is just E of X. This is okay, and I mean one should remember that rho of it's in like and it's similar for the other fields. So this is what if I had a fluid picture, this is how I would define the fields. But we'll use this description, the lattice description, which makes it possible to do many things sort of very systematically. Okay, so now what are the hydrodynamic equations? So so we'll start with the microscopic conservation laws, and then try to write the Euler equations and then the Navier-Stokes equation.
Really stupid question. In the row, what symbol is that for spatial?
This one?
Yes.
This is the, then what is it? I mean, here's the lattice position x equal to 1, 2, and so on. And then there is a physical space, right?
So is this like a small x?
That's small x right here.
Oh.
And, so now we see
So this again, just remind, so the QX though is the big X.
is the big X.
Big X.
That's the lattice. Yeah, sorry for this kind of confusing notation.
Yeah.
But capital X is always like integer, that is, and the X is like the real line. Okay, so now we write the hydrodynamic equation. So first at the let's say microscopic level, we just write the conservation equation. So then from this it's kind of trivial. So we see that Rx dot is plus plus 1 minus Q of X. So Qx dot is just Px, that Hamiltonian dynamics. And so this is in the form of so this is a discrete derivative right now. So del X of some current J and the field here. Where J
Perhaps, yeah. We are sure about that, your basic point. So usually hydrodynamic equations should appear after taking some limit, I think. But in this case, we are pouring some continued equation.
yeah, so this time just writing the conservation equations at the microscopic level, and then I'll show how to derive the usual I mean like the post grain.
and you're coding, coordinate equation.
Right, yeah, well, this is this continuity equation, right, and completely microscopic.
And the other thing is that you're not normalizing your relative energy by density. So
No, okay. So this I would, of course, I can define this as rho times the velocity.
yeah.
So, but this is my definition of it. Then if I want to define a velocity field, I would just write this as rho. So V would be the normalized velocity field, which is
okay, and typically also you do oftentimes have about energy density.
right.
Then we also have to define a rho times energy density part of my.
Yeah. So this energy density would include both the internal energy and also the flow rate.
Yeah.
So this this would be given by rho of let's say this square by 2 plus internal energy. So this is just the convective part of the energy, and then we will go. Okay, so right. Okay, so now yeah. So these are completely just I'm writing exact continuity equation. So it's still not hydrodynamic equation. Okay, so but this has the form. So I'm trying to identify what are the currents corresponding to the three fields at the microscopic level. So this is the current corresponding to volume, JP, which is so now JP is equal to minus P of X. Okay, then if I look at what is Px dot, so this just from the equations of motion, Px dot is minus and this H involves the potential, which is a function of Qx plus 1 minus Qx. So this will be G prime of. So Qx comes in two places, Qx involving x plus 1 and x minus 1. And prime is a derivative with respect to the argument. Okay, so now this is again in the form of a continuity so where that is the it's negative of this. So this is the momentum current, and these are the microscopic currents. This should be GR. So JP is equal to G prime of, so this is you can see the R of X. So R of X. And so this is the force between two particles. So it's basically the pressure. So I just write it with a hat because it's still a microscopic of the hat. Right? Okay, so this is the momentum current, and then finally I find the energy current. So if I do Ex dot, so if I do Ex dot, then again using the equations of motion, what one finds is that so this again has a continuity form, and this is minus the J energy. So
What's the big capital P?
oh, sorry, that's the pressure. So it's the force between two particles, right? V prime is the force between two particles. So that if I take an average, that's going to be exactly pressure. So right now I have not done any application, so I'm putting a hat, but it's the pressure operator. The hat. Okay. Okay. So this gives me the energy current JP, and this is just equal to Px times this, so it's minus. Small p is momentum, and then times this is capital P, so that's the pressure. Right? So it's momentum times pressure. So that's the energy current. Okay, so the stretch current is this momentum, the momentum current is pressure, and the energy current is momentum times pressure. Okay, so let's write the question problem. So these are the microscopic continuity equation. Okay, now if I want to look at Euler hydrodynamics. Okay, so these are the three currents. Then what one assumes is that as this long chain of particles, and so then I sort of do some course training over let's say cells of size L, and I assume that within each local cell there's local equilibrium, and which is described by the conserved quantities. Okay, so and so what are the conserved quantities? The conserved quantities are the average value of spread, then the average momentum, which I call and the average energy. Okay, so I now assume that these fields are varying slowly if I do some course training over some hydrodynamic landscape. Okay, so and then given this local equilibrium state, I should find the expectation value of these currents. So if I just assume local equilibrium and find the expectation value of the currents, that will give me the Euler currents. So basically, I need to find the expectation value of these three currents in a state of local equilibrium. And the local equilibrium will have finite values of stretch energy and stretch momentum and energy. And so this averages I denote by let's say U is the average momentum, and energy this called E, and this. So okay, so now I want the fact that earlier I was using microscopic variables, I was labeling by R, but from now onwards R will denote the like the average quantity, and the average momentum will be denoted by U, and energy will be definitely. Okay, so now given these are the currents, we can see that so what is okay, so the so indeed I should write the so I mean locally at least if I look at the distribution so this is the first case distribution of the particles. It will have a form. So writing the local ensemble is sort of important.
Just what are the averages here? You're
This
using
is over over this ensemble.
okay,
it's
you're
the
using
local-
Hamilton's equation, so it's
Sorry.
you're using Hamilton's equations.
Yeah.
So it's deterministic,
Right, yeah.
and it averages over the initial conditions.
No, so so now what I'm doing is okay, so so what I'm saying is that at any time this locally this place will be I mean you can define some this variables with expectation. Okay, so you ask what is the expectation? I mean
I think what's going to influence the noise.
yeah, I mean, I can think of maybe ensemble of initial conditions, and I'm doing an average over that ensemble. Right. So, and but I'm assuming that okay, see if I started from let's say an ensemble of initial conditions for which each of which give me the fields which are slowly varying. Right. So. I mean, these are microscopic variables, but I can calculate it's given an ensemble. I can calculate how it changes in space, right? Let's say at a given time. So I can do at a given time, this is let's say microscopic variable, and given any distribution, I can calculate it, right? Over DQs and DQs. Okay, so now this is not GQs, but I'm saying some distribution. Okay, so for any ensemble, I can compute expectation values. Right. So now let's say at time 0, I choose this ensemble in such a way that R has some profile, which is very slowly in as a function of X. It's a local, I mean, Gibbs distribution. Okay, now I mean this distribution of course will evolve with time. And at any time I can compute, but I'm assuming that at all times there is this notion of local equilibrium. Right. Okay. And therefore, I'm assuming that at any time I can have a description in terms of ensemble like this, where this pressure and temperature these are of course varying slowly in space and time. Okay, so now. Okay, so this is I'm just writing it in this small cell. Okay, and then this equilibrium. So this is the ensemble over which this average is computed. Sorry, I should be just. Okay, so now I introduced this pressure, like in the, I'm choosing an ensemble where Rx is fixed on average, so that's why in a pressure term. So yeah, so this is the ensemble where pressure and temperature are fixed, and also the local fluid velocity. So in this ensemble, I compute the local currents, assuming this local equilibrium state. And so if I now compute this object, what I find is that this is equal to just minus u, right? This Px average for this ensemble is just minus u. GP average would be that's just the pressure, and J energy average would be minus u times. Okay, so now here I have to remember that the pressure is so if you look at energy in this ensemble, that has two parts. One is one just comes from the fact that there's a flow energy, so that will give me so the internal energy is really I find yes. So this kinetic energy is so this is really the internal energy. Okay, then there's some flow energy. Okay, now the pressure will depend on this part. Right? I mean, I should subtract from the total energy. I should subtract this pressure, right? So this pressure is pressure here is the function of the energy after you subtract this is function of E minus and it's a function of the stress. Okay, so what I want is that so these are the Euler currents. They should be expressed in terms of the conserved fields, and this is what I've done by just assuming local equilibrium. Okay, so now everything depends on U, E, and R, like all the currents. I hope this is.
And so this local equilibrium, I mean, I can see that the term there is like an expand, it's like a Taylor series expansion of V of R about
No.
our half, does it? Looks like it.
No, sir. So this is.
So the definition of your.
I don't see that.
Yeah, that would be that.
This is the pressure
This is the actual pressure.
right. Yeah. So I'm now working in an ensemble where temperature and pressure are fixed. So that's why I introduced this term. Like it says pressure times volume.
Okay.
So I could have worked in a microcanonical volume fixed ensemble, but it's more convenient to work in an ensemble where the pressure is fixed. So I'm just changing from microcanonical to canonical ensemble with pressure fixed.
And when you see, then you must have a way to calculate pressure self-consistently.
Right. Yeah. So, but pressure, given so let's if I just have this partition function, Then of course, so it's a function of some pressure and temperature. Now I can always ask like what is given this distribution, what is the average stretch arc and what is the average energy, right? And then I can just I can compute pressure as a function of the energy and stretch, and so I can I can go between variables, right? Between this sort of
And you can do this because it's just in a infinite. Large.
it's infinite, or and also it's its product measure is exact. But that's one of the interesting things that like the important thing that the full distribution has a product measure, so I can do everything kind of exactly.
So you don't need to, it doesn't need to be a large hand.
Okay, so eventually, of course, the hydrodynamic description relies on, but at this level, I could do everything.
So the only assumption is that you have a local equilibrium.
Right, yeah.
Given by this distribution.
Right. Okay, so yeah. So, okay, so now I therefore my Euler equations. And so now everything is after taking an average in this local equilibrium ensembles. So so I have DC over the so now these are no longer operators, these are just averages, and they're given by minus 10. So the first current is just minus Ux, and the second current is the pressure, and the third current is and here everything is expressed in terms of this field. So, so Ux is already there, and like I said, the pressure is computed just from equilibrium. There's the equilibrium partition function where I need to replace. So instead of this is the actual total energy, but I have to subtract the flow part. So this I should do. So now the pressure is also expressed in terms of the fields. Okay, so so these are the Euler equations, and now so okay, I should say that this is completely equivalent to so. Okay, so these equations. So let me just write these equations. So this is, I think these are more well-known equations. So these are the usual Navier-Stokes equations that one writes for a fluid, and one can transform from this to this by just using the fact that this is this x is a local variable which moves with the particle, while this small x is the like fixed space variable. And the transformation is basically given by something like if I write if I count the number of particles, let's say from 0 to x. So this will basically give me x. So which means that rho okay, so this gives a transformation between the local variable and space variable. And using this, one can go from this set of equations to different equations. Okay, but this is what was first used to analyze this hydrodynamic equation. So this is the I think it was first written in Harvard Spohn's paper in JFP. Okay, so for this anamorphic change, this is somehow much more convenient description because you can do the subsequent calculations very accurately. And it's more convenient.
Sorry, so I think so you about and like is
Sorry,
zero.
I just took a derivative of this equation. Okay, so now what will be interested in, so let's say we introduce the fields, so that for them fields. And what we want to look at is like, and then so we want to look at the fluctuations in equilibrium of this fields. So okay, so if we first look at these equations, the equations, and since we're looking at fluctuations in equilibrium, we can let's expand the fields around the equilibrium values, right? So so we have some equation like and now we want to expand this around the equilibrium value. So this currents is so if we expand, then the equation that we get is so this is some matrix which depends only on on the equilibrium values of the fields and not on space time. Right? Just something in there. So then this equation of the structure is so where this matrix A is just obtained from purely equilibrium thermodynamics. So now, then the standard thing to do out here is just go to to diagonalize this matrix A and find the hydrodynamic modes. So basically, I try to find the matrix R, which diagonal is the matrix A, and let's say I call this matrix lambda. And one can show that this always okay. So yeah, it's easy to show that this has always real eigenvalues. And in this case, for dynamic change, it turns out that this the structure for diagonal matrix, which is minus B 0. So these are three eigenvalues, which are two of them are just negatives of each other, and one is 0. So if I now make a change of variable and define fields phi minus 1, phi 0, and phi plus 1 is equal to and see that this equation has a point in 2. So see, this is A goes from this one to
R times B.
phi is phi is okay. So I'm just making a linear transformation from U to going to the diagonal basis of this matrix. So that's how I find the normal.
So yeah, it's minus C0C.
Minus, so if I diagonalize this matrix A,
Yeah.
the eigenvalues turn out to be minus C0C.
Okay, it's always.
It's always at least for the dynamic change, it's always like right here. So recently, actually, we are looking at some systems which might have different states and so on, but at least for the QT chain, it's always like okay. So now these are now uncoupled equations, right? And the solution is that we just moves that which means if I look at the correlations of these fields, they have right. So if I look at the correlations between the fields, so let's define them as a and the correlations in the original variables, I define them as intertilde, and so these are. So these are all equilibrium correlations. So this is in the original fields, and these are in the transformed fields. So they are of course related. So now this one, once I have the structure, what it tells me is that there are three modes. And one mode is this fixed, so this is space, and I'm talking this position function. So at one mode just is the delta function at x equal to 0, and there are two these are the sound modes which travel with speed c, and this one and okay, so the other at t equal to 0, the correlations are, because I have a product measure, so the correlation functions are it's I mean it's a delta function. Okay, so, so this means I should say that is a b at x times 0. So the equilibrium correlations at time 0, that's the it says delta x0 times some correlation matrix C of A. And then which time they just travel as delta function peaks to sound peaks, and that's over. Okay, so now in while writing, so the next thing one does is to include the dissipation in the hydrodynamic equations. So these equations, I mean, at the Euler level, I'm neglecting dissipation. So if I introduce dissipation, then so. So I'm now writing the largest group. Then this equation gets modified to then I just add dissipation. I mean, clearly at a phenomenological level. So this is the sort of usual expected form of dissipation. And this B and D satisfy some fluctuation dissipation relation, which ensures that the equilibrium correlations are preserved. And so
theta does not depend on alpha or beta.
sorry.
Theta doesn't have a component.
These are the big B in front of it.
Then the correlator should also.
Sorry.
It's up,
It's a correlator.
Sorry. Okay, and D and D have to satisfy this fluctuation distribution theorem, which is okay. So sorry, I just use some different notation. We call this in the because I want to use skip D and D for the when I go to normal modes. So fluctuation distribution theorem says that so if I just put the requirement that this equation keeps the initial correlations unchanged. So initial correlations are so then I put a detailed idea invariant, then it gives me this condition.
and the filter that is transport.
Transport, right. That's
Right.
right, yeah. Yeah. Except for real. Oh, is it like that?
Okay.
Yeah, yeah. So I'll just say what I'm going to do. So I'll take 2 minutes. Okay. Sorry. So now basically what one sees is that at the linearized level, if I introduce distribution and noise, then what's going to happen is that the squares are going to broaden. So they will get spread diffusively. So I'll get diffusive peaks for the two sound modes and the peak mode. And then the observation is, of course, that they are not diffusive. The spreading is anomalous, and that we will try to understand by just going to the next order terms in the expansion. So this is a linear order. Now we'll keep the next order terms u square, and that we'll see that what it will give eventually is that this sound peaks are going to behave like APZ mode, but the heat peak is going to have a lazy form. Okay, so this is that's how the nonlinearity works. Okay, so this will try to understand in the next lecture, and then we'll go on to the spin chains.
Okay, thank you. Any questions? Comments? So A is a function of, generally a function of X, will it?
A is not a function of it. A is just it's because it's in the equilibrium. So it's the function of pressure, temperature, and volume.
Yeah, and that's because of somehow transition variance that we've seen that it doesn't matter where you are along the chain, probably the same.
Right, yeah. I mean, and it also it's in equilibrium, right?
Yes,
yeah. Complicated in equilibrium. So that's
Sometimes people like this is shown in this kind of form where this is the form that depends on field and position.
right, yeah. So that I could do that.
Yeah, yeah.
But
Logically,
yeah,
well.
like for example, integral system that is good on right, but here it's yeah, it's completely independent of the fields.
But that's because of the model, that's because we started off with a model which basically, we started off with equilibrium, saying that, you know.
In equilibrium, and I'm doing an expansion around the equilibrium, right? So I'm just writing things linear in the fields.
Yeah. Yeah, yeah.
What extent is the initial derivation dependent on having just nearest neighbor interactions and not next neighbor?
Yeah, so here of course like a lot of I mean a lot of the steps do depend on just nearest neighbor.
The answer you expect to be inverse.
Okay, so people have looked at, for example, and if I take a Lennard-Jones interaction with all two over here, I mean, so you still seem to get the same analysis feature and same exponents and so on. But at least this derivation would break down. I mean, at least I mean, it seems to me now. I think.
But sometimes some kind of approximation, but if you have next interactions, they somehow will be there, and you have to have second order derivatives in your equations. I guess that you need to do things to because the reason you have first order, your d by the big X is essentially p something plus x plus 1 minus something x. You know, in your current equations there.
Right, yeah.
Yeah,
So
yeah.
I mean, see, for any, I mean, like at least like these equations would definitely be of exactly the same form. Only thing about it would become difficult is like I wouldn't be able. I don't know very much about the equation of state and so on. But these equations are definitely true for even the like any range of interactions and so on. But the lattice description becomes more complicated. But at least at this level, it's similar.
Other questions? No? I have one. So how reliable are these equations, the final equation? You know, it's kind of derived, but The whole equation seems more or less okay, but.
For this,
Basically, so these.
yeah,
these
so
are by hand.
by hand, right, yeah, so deriving, I mean, this from microscopy is very highly non-trivial because. I mean, for example, transport coefficients are usually given by Green-Kubo, right? But in this case, we know that Green-Kubo gives a divergence.
Right.
Right, so it's not, it looks like inconsequent. So this is, I mean, the idea is that these are sort of at a mesoscopic level, this transport coefficient. And then the divergence come at the hydrodynamic level. Okay, so then this has to be defined at some intermediate scale. And so this is something that I have a paper with KG and Sanda, and where we try to sort of derive this from microscopic, but it's, I would say it's kind of, it's not very clear, I mean, it's not a clean derivation.
I'm also always wondering about this. There's a function alpha beta. So this is also kind of assumption that
Yeah.
for the normal rules, these images are independent.
Right, yeah. At the, this is even before going to normal.
So sorry, before.
Right, yeah. And that of course, like from some central limiting, you expect that different modes, okay, it's not. It's not very.
So we have to try to compare with the simulation and the prediction from this kind of equation.
Right, yeah, even that is not done, like if you really want to look at the detailed effect of this term, that's it's not yet satisfactorily done.
Okay, thank you. Other questions? Okay, so if there are some further informal questions, we can of course remain, but for the moment, let's stop and let's not.